All right, lesson 1-4. Today we're going to look at identifying key characteristics of polynomial functions. So a polynomial function means that there's going to be multiple terms. So if you're wondering what does that polynomial mean, that means there will be multiple terms. Multiple terms. So as an example here, y equals x squared plus 7. That has multiple terms. It has two separate terms. Or here's another, y equals negative 5x cubed plus 2x minus 2. That right there is another polynomial. There's multiple terms. This has how many terms? How many terms are there? Do you count? 3 terms. I hear someone whispering it. You can go ahead and say it. 3 terms. How many terms was here? 2. When we talk about polynomial, we're talking about multiple. That means more than one. More than one term. That's what's going to be our polynomial functions. We're going to talk about those today. So equations that are in this form. To begin, let's start off with a couple of rules here. A polynomial function in general form will look like this, where you see these a sub n, a sub n minus 1, a1, a0. These are all what we call coefficients. These will all be numbers. The a values are numbers. Specifically, the very first number cannot be a 0. So your last number can be a 0, but not your very first. An represents the first value. This right here is called the leading term, and it cannot be 0. And the leading term, and it cannot equal 0. That's what this is saying up above it. So I'll add that in. So a sub n times x to the power of n is called the leading term. So the leading term is the highest powered term. The an is the leading coefficient. N is the degree. That's a key word you're going to hear a lot, degree. The degree means the highest power or greatest power, it says here. That's your key vocabulary. This is the key vocabulary term. Key vocabulary term. Degree. So what does degree mean when I say degree? It's the greatest power you see in the equation. Okay, the a0 is just the constant. That's if there's a number at the end. So like in this case, it would be plus 7. In this case, it would be minus 2. That's what the a0 is. I already told you this. The a values represent real numbers. And domain is all real numbers. Does anybody remember why from lesson 1-1? The domain will be all reals. Does anybody remember why it would be all reals? There were 3 rules. You remember what the rules are? You can cheat my class. That's your hint. On the domain rules, there's a way to cheat my class. What's the way to cheat? Okay, you're looking for divisions. Do you see any division symbol up here? Because you're not allowed to divide by 0. And there's no division, so I can't break the domain that way. Next, you look for square roots. Do you see any square roots? Nope, there's no square roots. Do you see the word log anywhere? Because there's no divisions, no logs. The domain is going to be the set of all real numbers. I'm going to go ahead and add that in. I'm going to type it in so it's easy to see. Because there is no division of x, no square root, and no logarithms. That's why the domain is all reals. How about I put all domain is all reals? How about I start complete sentence? The domain is all reals because. There we go. I'll make that a little bit smaller so it's easier to fit it all in there. Okay, so that's why the domain is all reals. Those are the 3 rules that we will need to have down before your first test rolls around. Those are something you'll need to know. It's what you search for to see if something's all reals. Do I see any divisions with x? Do I see any square roots? Do I see any logarithms? Since the answer is no on all of those, it's all reals. Okay. There's one more slide that I have that's kind of just a general thing to help you out. A little diagram. is this one. Here's what it'll look like with numbers plugged in. This right here, I say the degree is 5. What does it mean if I say degree? That's the greatest power. Look at the powers. 5, 4, 3, 2. That's like a power 1. That doesn't have any powers at all of x. It's like x to the power 0. So they count down 5, 4, 3, 2, 1, and this has no x's, so it's like x to the 0. The highest power was 5, so we'd say that's the degree. The leading coefficient is the number that's in front. Coefficient means number. And 3x to the 5th would be called the leading term. So those are all vocabulary terms you might hear. The coefficients, like I said, are the numbers in front. And the constant, that would be where it hits the y-intercept. So this constant coefficient, if you want to include that in there, is a y-intercept. Is the, not a, it is the y-intercept. So whatever your constant is, that's where it will cross the y-axis. As stated in the last page, polynomial function has no variables in the denominator. We call it a different function if it has variables in the denominator. That'll be later in this 6 weeks or this 9-week grading period. We're going to learn about this, but not yet. It'll be after the first test. If you have a variable in the denominator, it's no longer polynomial. We call it something else. Next, the exponents cannot contain fractions or negative numbers. They must be whole numbers for polynomials. If they do, we call it something else. And you'll learn about that as the year goes on. Okay, so there are your general rules. Now let's just do some math and let's see what we can determine about these. Okay, so example 1. Example 1 says determine whether each of the following functions is a polynomial. Explain your answer. So based off the rules that I just gave you, you can cheat because you have a packet. You can look at this slide and this slide, or you can look at this slide there. What do you think when you look at part A? Is this a function or not a function? I'm sorry. Is this a polynomial function or is it not a polynomial? I hear it's not. What makes you say it's not a polynomial? The power is a fraction. By the way, if it's on the constant that does not have an x, that is okay. It's actually okay on this scenario. It's not here. This makes it not a polynomial. This would actually become a radical. This is where square roots and those things come from. This would be a radical. It's not actually a square root, but that's what that comes from. This is not polynomial since x has a power that is a fraction. Two divided by 3. So you know what I'm talking about there. Now, what I was saying here is that -2 is okay. If it's on the constant, it's okay. If it's on the constant, that means the value without an x. It's okay to have, I'm going to call it a weird power. It's okay to have weird powers on the constant. That is allowed. It's just on the powers of x that you have to be whole numbers and they must be positive whole numbers. Okay, let's go to the next one. Part B. What do you think? Is this a polynomial? No, very good. Why is it not polynomial? It has a radical. You're not allowed to have radicals when it comes to polynomials. So for 2 reasons, this one and this one, this is not polynomial. This is not polynomial since x is inside a radical or a root, whatever you want to call it. Whether you want to call it a radical or a root. That's like a square root, that's a third root. You're not allowed to do that. That's the square root and third root. That's the reason why. That is not polynomial. All right. As we go on to the next page, what do you think about C? What do you think about C? Polynomial, not polynomial. This is not polynomial. Very good. This is not polynomial. Why is it not polynomial? What's the part that throws it off? The X is in the division. Yeah. This is not polynomial. This is not polynomial because X cannot be dividing on a polynomial. Now, X is allowed to divide, but we just don't call it polynomial. You're going to learn it's called rational. So this one is not polynomial. We call it rational. That's going to be the word because X cannot be dividing. Now, the next one I'm going to tell you right now, it's a trick problem because we need to first simplify. Let's simplify g of x. Okay, so how could I simplify g of x? I could say g of x equals, what's x cubed divided by x? I'll give you a hint. X cubed is like this. X cubed over x is the same thing as writing x times x times x divided by x. What could I do if you looked at it this way? X times x times x divided by x, which is going to be equal to x squared. So g of x is going to be x squared plus, and here's a weird one. This right here, 2 over x to the negative 2. When you have a negative power, what that means is you move it from the denominator to the numerator or vice versa. So 2 over x to the negative 2, that's equal to 2 to the power of x squared over nothing. When you see a negative power, you flip it from the numerator to the denominator, or in this case, from the denominator to the numerator. That gets moved up and you drop the negative. So if you have nothing left over in the denominator, what do I put down there if there's nothing left over? A 1. And so what would this be equal to? 2x squared. Okay, continuing on. Do you know what you do with a square on a square root? Square root and a square. What's their relationship? They cancel each other out. This cancels and this cancels. What are we left with? X. Those cancel each other out. And finally, do you know what anything to the 0 power becomes? Anything to the power of 0 is 1. Okay, when you look at that, is that polynomial? Is this polynomial now? Yes, it is. And actually, you could rewrite it one more way. What's an x squared plus 2 more x squareds? Good thought. That's if it was multiplying. But this is, when you add, it's like saying, hey, I have 1 x squared plus 2 more x squareds. How many x squareds do I have total? 3. Yeah, when you add and subtract, you don't change the power, or you just change the quantity of that power. So I have 3x squareds plus 1x plus 1. That right there is polynomial. After simplifying, this is g of x, I'll just say g of x is a polynomial. So after simplifying, we can see that g of x is in fact polynomial. So do you understand how the rules work a little bit? Thomas says no. All right, what you cannot have is you cannot have x's that are dividing, You cannot have fractions of powers on x. You cannot have radicals for polynomials. This one was a tricky one. This is a tricky problem. I'm not gonna lie, it was tricky. We had to simplify it here. And so we first divided out the x and realized, okay, we no longer had the division, it just became x squared. Over here, a negative power, you can shift it to the numerator, become positive, and once it's in the numerator, now we have no problems. Once it's in the numerator and a positive power, we have no problems. Here, the square root canceled, so that wasn't an issue, and this just became the number 1. That's why that one worked, but it was a tricky problem. I'll tell you right now, you will not see any of this tricky later on. Okay, so, yep. When you have a negative power, it's almost like, instead of saying, hey, I'm dividing by x to a negative power, dividing by x to the negative power is the same thing as multiplying by x to a positive power. I'm gonna write that out so you can see it. Dividing by x to a negative power is the same thing as multiplying by x to a positive power. Okay, so there's the words. And I'm gonna highlight what I want you to know. Okay. Dividing by x to a negative power, and I'm gonna hit the dividing. Dividing by x to a negative power is the same thing as multiplying. What am I missing here? Multiplying by x to a positive power. That's the math rule. I'm just gonna go ahead and put this on the previous page. That's a good thing to have adding in there. And so I'll need to shrink it. Sorry, I'm getting our notes in order. Let me move this down. Oops. So it's not all covering up. Come on, where is it? All right, so picking back up here, we have our first DOL. I want you to determine whether this function is polynomial. Now you'll need to simplify. Simplify it. What does it mean in mathematics whenever you see a parenthesis? You're gonna have to multiply. I need you to multiply it, simplify, and see what you come up with. DOL number 1. All right, another slide of rules. I'm not going to, you can read these later on, but basically what it's saying is we'll call different functions by the highest power. For example, if you have something that says y equals x squared, what type of equation would we call that? You've learned this in the past. What would you call something with the highest power x squared? Starts with a Q. Rhymes with quadratic. You'd say this is quadratic. Okay, if the highest power was a 1, what have you learned that's called if it's the highest power 1? Linear. That would be linear. Okay, how about this? What if it was x cubed? We call that cubic. That's what this slide is telling you, and you could predict the shape based off of that. Quadratic would be a parabola. A linear would make a line. A cubic makes an S-curve. That's what this slide is telling you. That you can predict a lot of things based off the highest power, the degree. So you look at the degree. That's what you're looking at. That's what this slide is telling you. So with that, we can take some look at some examples here. By the way, these are continuous. That's why there's no domain breaks, because there's no division of x's, there's no square roots, there's no logarithms. So since the domain will not break, it'll be a smooth line, a smooth curve that you can draw without picking up your pencil. Okay, so here it says identify whether each of these is a polynomial or not a polynomial just by looking at them. What do you think on this one? Would this be a polynomial or not a polynomial? Not a polynomial. How do I know? It breaks. Are you allowed to break with no domain issues? No, you're not allowed to do that. So since there's breaks, this is not polynomial. This is, I know it just says N or P. I'm gonna go ahead and just write, it's not polynomial, because you see a break. What about the next one? What would you say about part B? It is a polynomial. Why is it polynomial?
It doesn't break.
There's no breaks. There's no breaks. Hey, help me out here. The interval to the left of this vertical line, concave up, concave down. Concave up. I actually drew this in the wrong spot. Whoops. I put this in the wrong spot. Let me. Concave up or concave down right here? Up. Concave up, concave down. And let me slide it over to the right spot, about right, maybe in there somewhere. Concave up or concave down in there? Concave down. And finally, how does this end? Yeah, that's just a review. We call this concave up. This would be concave down and concave up. What does it mean if a function's concave up? What can you tell me? Okay, I hear increasing. What is increasing? Just to say it's increasing is not enough information. Concave up. If something's concave up, what is increasing? Here's slope. This is a curve. It doesn't have slope. What do we call it instead of slope? AROC. The AROC is increasing. And we learned last class one more thing. So not only is the AROC increasing, you can tell me about delta AROC. This is what we learned last class. What is true about delta AROC? It's positive. Very good. Delta AROC is going to be positive. It's concave up. AROC is increasing. Delta AROC is greater than 0. Finally, and I'm going to just do this one more time. What can you tell me if it's concave down? If something is concave down, AROC is decreasing. And if your AROC is decreasing, what can you tell me about delta AROC? It's less than 0. It's negative. Remember, delta AROC is 0 at the inflection points. So in the inflection points, when it changes from concave up to concave down, that's where your delta AROC would equal 0. Okay, that was a review from last class. That was 1-3. That's what we talked about with the 1-3 was delta AROC. Okay, let's take a look. I'll let you flip your page here. Let's take a look at the next example. I think I got 2 more of these. Part C, what do you think? Polynomial, not polynomial? This is not polynomial. Polynomial will never have sharp points. They call these mathematically a corner or a cusp. They will not have that. That is not polynomial. Polynomial will be smooth. It can change directions, but it'll do so in a smooth manner, not as a point. Not polynomial since the graph contains points. If you see points in the graph like this, like pointy edges, that would not be polynomial. Okay, what about the last one? Polynomial, not polynomial. This is polynomial. Why is it polynomial? It's no breaks, no sharp edges. Polynomial. All right, as we move forward, there are some key functions we can talk about. We've already talked about the domain. What should be the domain of a polynomial? It should be all reals. So we talked about that. You can write it either way. You can, polynomial domain should be all reals. So that should always be true. Zeros. Here's something new. When we talk about the degree, the maximum number of zeros will equal the degree. The zeros, what is a zero again? X-intercepts. So the zeros means x-intercepts. So the maximum number of x-intercepts, maximum number of x-intercepts equals the degree. And what's the degree one more time? The highest power. Now this says maximum. Does it mean you always are at your maximum? No, I'll give you a quick example just to show you what I mean. On the next slide, here we go. If you had an X and Y axis, you can just sneak this in if you want. Notice here's the graph that's X squared. That's a graph that's X squared that's been shifted up. Let me just say it's X squared plus 3, so I better put it on the Y axis. Let's say it was X squared plus 3. What's my degree right now? 2. That means I should have 2x at max, 2 x-intercepts. Do I actually have any x-intercepts at all? No, so you don't have to have them, but the maximum number you could ever have is 2. And just think about it. If I shifted this graph down, now how many x-intercepts do I have? 2. The most you could ever have is 2. So whatever your power is, that's the maximum number of zeros. Okay. We talked about if it's increasing, that means it goes up as it travels from left to right. Let me delete this slide. Don't need that anymore. Decreasing if it goes down from left to right, concave up, concave down. We just reviewed that a moment ago. Inflection point when it changes between concavities. Maximum and minimum are any of those points when you're concave up or concave down. When you reach, this would be a maximum. This would be a minimum. This is another maximum. This is another minimum. So maximum does not mean the entire graph necessarily. It just means you're at the highest point of concave down or the lowest point of concave up. That's what it means. Okay. So that's your maximums, minimums. And absolute, if they say absolute max or absolute minimum, that means it really is the highest point in the graph or the lowest point in the graph. That's the only difference there. You can read over those on your own leisure. Okay, so here's a diagram just to help give you points to help you out. If you're at home, you can look on this at home. Notice how many zeros do you see? 3. If you see 3 zeros, what do you know has to be true of the equation? It has to have at least x cubed. It could be more. And this one would have to be an even number. You'll learn about that in a second. How do I know it has to be even number? It goes off the screen like a parabola. If they go both pieces going up, you would call that, it has to be an even power. It's not going to be odd. Odd goes diagonal off the screen. One up, one down. This one goes off the screen up both ways. So it has to be an even power, and it has to have a power that's bigger than 3. Okay, so usually you'd say greater than or equal to 3. In this case, I know it has to be odd, even powers, so bigger than 3. Okay, here we go. Let's take a look. Let's see what we can determine first, and then we'll graph to get the rest. What could you tell me is true looking at this picture here? Could you name what type of polynomial it is? Could you name it taking a look at the function? Not linear. Good. It's quadratic. Why is it quadratic? Since, what's the degree? What's degree mean? Highest power. What's the highest power? 2. It's going to be quadratic. It's going to look like a parabola. Let's go to our calculator. I told you we'll use your calculator today. Let's graph this. I'm going to go home screen. Don't save. Hit add a graph. The equation is x squared plus 4x minus 12. Now, this is telling us we're only going to be concerned with -8 to 4. So I got to show you a calculator trick. So I need you to type this in. If you don't have a calculator, go get one. Type this in and then don't press enter. I got to show you a calculator trick. So it only graphs from -8 to 4. Now in pre-cal, these are called a domain restriction. That means it's going to cut off the graph at -8 on the left and +4 on the right. Our calculators do this really well. Here's how you do that. Hit the control equals button. So after you type in the equation, I want you to hit control equals. If they give you a restriction, you're going to hit this vertical line. You see that vertical line in there? Hit that vertical line. And now we're going to say -8. In the calculator, you always have to use these symbols. Is less than or equal to x, which is less than or equal to +4. Let me slide this over so you can see better what I just typed in. I typed in this vertical line, which is in the control equals button. I did control equals. That's where I saw that. It's called a pipe. So if you ever hear me say press the pipe, type in pipe. That's what that is. It's control equals that vertical line. And then I did -8 is less than or equal to x, which is less than or equal to 4. After you type all that in, press enter. Okay, and what I'm going to do is I need to be able to see a little bit more in this graph to get all my values. So I'm going to zoom this out. Here's how I'm going to do it specifically. I don't want to go too far. I'm going to highlight the 6.67 at the top of my screen. I'm going to double click it, and I'm just going to press 20. I'm going to type in 20 there. I'm going to press enter. And we'll go to the bottom of the screen, and I'm going to type in -20. I see that I still can't tell the top of the graph. I'm surprised. I thought I was going to be able to see. Maybe I need to go to about 40. I'm going to type in 40 on the top. I'm going to go back to the y-axis. I'm going to double click it and tell the y-axis to graph up to 40. There we go. That's enough. I can now see the top of the graph. So I typed the top of the, I hit the top of the y-axis. I typed in 40. I did -20 on the bottom of the screen. I do not use the zoom out function very often in our calculators because I usually don't want to change the y values. I typically want to keep my y values the same. What you can do is zoom fit if you prefer, but I don't want to change the x values. I just change the y's typically. Okay, does everybody have a graph somewhat looking like mine? I'm going to show you how to use calculator tools to find everything we need. We need to establish where the zeros are. We need to find these maximums and these minimums. So go to your calculator, press the menu button. Choose Analyze Graph. The first option that comes up is 0. Let's find the 0. So click 0. What that does is it's going to give you this dotted vertical line. You need to click, when it says lower bound, that means you're telling the calculator where to look. You just go to the left of the first 0. Lower bound means the number smaller. So just go to the left of this 0 right there and click. It doesn't matter how far over, just go to the left of it. Once you click the center button, it'll change from lower bound to upper bound. As long as you go to the right, it's going to find that value. Are you getting the value -60 like me? Perfect. That's 1, 0. Let's do it again. Press menu. Let's find the other 0. I know you can see it, but I'm going to do it anyways. Analyze graph. Choose 0 again. This says lower bound. So you're going to go to the left of this 0. I go to the left and I click. Once I click, it's going to change to upper bound. Well, let me come on this side. Now that it says upper bound, I just need to go to the right of that 0. Once you click again, it'll give you that value. Are you getting +2, 0? Are you getting that same value? Great. We got 2 values left. We need to find, actually, it's going to be 3. This minimum and these 2 maximums. So hit menu, go to Analyze Graph, choose minimum. Again, it says lower bound, so go to the left of the minimum, click. Go to the right of the minimum, click, and it'll give you that value. It's telling me it's -2, -16. Last time around, I'm going to find my maximums. Menu, Analyze Graph, choose maximum. So a maximum should be the highest point of concave down, or I should have said this earlier, an end point. An end point is where the graph ends if you have a restriction, and we would count that as a maximum. That's going to be a maximum there because it's the highest point in that area. And over here we have another maximum. So I'm going to go to the left, I'm going to click, go to the right, and I'm going to click. You should have got the same values as me. Now that we have all those values, we can write in, and I'm going to show you how you write your answer. When it says zeros, you do x equals and you say what the values are. What are the x values that we had zeros? -6 and 2. That's how you would write that. -6 and 2. Now, as it concerns maximums, if it says absolute, that means it's the highest point on the graph. If it says relative, that means it's the highest point in an area. I have these 2 maximums. Are these the highest points of the entire graph, or are they just the highest points in the area? So the graph goes higher somewhere else? Or is this the highest point the graph ever gets? That's right. 20 is the highest it ever gets. So those are going to be both absolute maximums. Here's how you write that. It's going to be tricky here. Okay. We're gonna say f of -8, f of -8 equals 20, comma, the other one is f of 4 equals 20. I'll explain this. We normally write y equals f of x. What did I replace the x with here? The x value of -8. What you do is, it's basically, I'm just putting the y value after like that. That's the y value. That's what I wrote there. Okay. So those are the two maximums. We don't have relative this time. We're gonna just, I'll do NA. We don't have relative, we have absolutes. You could actually list them if you wanted to. It wouldn't be wrong, but specifically since I have absolute, I'm gonna just put none there. Okay, tell me about the minimum. Is this a relative? It just means the lowest in the area, or is that the lowest in the entire graph? Okay, so we're gonna put it in as an absolute minimum. So you tell me, how would I write this value? Okay, you start with f. F -2, good. Equals -16. We don't have any relatives, so I'll do NA, not available. Okay, is the graph ever decreasing? Are you sure? From left to right, it's never going down? It's going down from where to where? Talk x values. You always do x values from -8 until -2. So it's decreasing. For increasing, decreasing, they usually just use parentheses. They'll never use brackets. It's not wrong if you do use brackets, but that's just how the test, that's how they'll give you answers. From -8 to -2, from left to right. Okay, what about increasing? Did the graph ever go up? From where to where? To -2 to 4. I think the reason why they don't use brackets on these is because you see how this is saying -2 is decreasing, and now we're saying it's increasing. That can be confusing. So I think they just use parentheses. So it's just like, okay, just in between 2 and 4, it's increasing. In between -8, -2, it's decreasing. Okay, is this graph concave up or concave down? Up. From where to where is it concave up? Where does it begin being concave up? -8. When does it stop being concave up? 4. So the whole domain. So -8 until 4. Where is it concave down? Nowhere. NA, not available. If it's not, if it never changes from concave up to concave down, what do we say about inflection points? There's none, not available. There's not any. I put NA, you can put none, that's fine as well. Go ahead, take a pass. All right, let's take a look at part B. What could you tell me, looking at the equation, what would you name it? All right, let me start with, what's the degree of the part B? 3. What's it called if it's third power? Cubic. So cubic since degree equals 3. Okay, let's do this again. I'm gonna just totally start off with my calculator. I'm gonna press home screen, that'll give me a new document, or home screen, and now I hit new. I'm gonna hit don't save. That'll clear out all my little stuff that we've done. Hit add a graph. X. I'm gonna hit the little caret button, is what you call that. It's not right next to x squared. It'll give me a power, and I can type in 3. I'm gonna leave the power and press +1. Before I hit enter, how do I type in the restriction from -2 to 2? Control equals. Now you choose the pipe. Let me go bigger so you can see what I'm doing better. I'm gonna hit that pipe and control equals. Type in -2, and for the calculator, you have to use inequalities. -2 is less than or equal to x, which is less than or equal to +2. Now press enter. Okay, this graph, the math is a little bit easier for me. I don't have to guess. We're gonna need to go as high as 10. So type in a 10 down up there. So we can see the top. Make sure we can see underneath, we're typing a -10, and we should be able to see both the top and the bottom of our function. Okay, this graph, what do I see? Do I have a 0? Did the graph cross the x-axis? Yes, hit 0. Let's go to the left of the 0. Let's go to the right of the 0 to get that point. The next one I asked for is a maximum. Does this graph have a maximum? Let's see here. If I go to maximum, let's see if this point has a maximum. I'm going to click to the left. I'm not sure if it does. Let's check it. I'm going to go to the left, and I'm going to the right. Does that inflection point create a maximum, or does it just continue to move as I go to the right? And it continues. So there's not a maximum there. So we keep on going. The only maximum this graph has is right there. That's the only maximum. So this inflection point is not a maximum on this problem. It doesn't actually curl down. Do I have a minimum? Does this graph have a minimum? Yes, it does. Menu, analyze graph. This time we choose minimum. Oh, I didn't realize the order was off. Minimum came first. Okay, let's do minimum. This right here is a minimum, and you can cross over and you see there's no minimum there at the inflection point. I think that's all the things we can add on. So I'm going to take a picture of that and add it over to our notes now. I think that's everything we'll need for this problem. I could be wrong, but I think it's everything we need. So let's fill it in. Do we have zeros? You said yes. How many zeros do you see? 1. So how do you write answers for zeros? X equals -1. The reason you can write this way is we know the y has to be 0. You don't have to tell it the y, because if it's zeros, it's telling you the y is 0. Do we have a maximum? What type of maximum? Is it relative? It just means in the area, or absolute? It's the highest point in the entire graph. It's absolute. This one we have to tell the x and y. So we'd write it as f of, which, yeah, what is x? 2. F of 2 equals 9. We don't have a relative maximum. Did this graph have a minimum? What type of minimum did it have? An absolute. So it's f of -2, whoops, -2, which equaled, we did not have a relative. Does this graph, as you go left to right, does it ever decrease? Where does it decrease? It actually never decreases at all. Never decreases. So if it's never decreasing, what's the curve always doing instead? It is strictly increasing. That means it's increasing the whole time from -2 to +2. It's increasing from -2 to +2. And like I said earlier, even though we have brackets here, when you do increasing, decreasing, they only use parentheses. You're not wrong if you put it in there. I'm not going to count you wrong. But technically, on increasing, decreasing, you only use parentheses, as well as concave up, concave down. Okay, tell me about this graph at the start. What's true of my average rate of changes? Are they always increasing or decreasing? Because is this concave up or concave down to begin? It's first concave down. It's concave down from, where does it start being concave down? -2. When does it change? What x value does it change concavities? Right there? Right here? What x value? 0. I think it's going to happen at this point there. If that y-intercept, I should have put the y-intercept on there. 0, 1. This changes concave down. It's only concave down from -2 to 0. What happens starting at 0 going to the right? It's concave up. So let's concave up from 0 to 2. Do we have any inflection points? Yes, and I'm going to write it this way as well, like I did the absolute maximum. I'm going to say f of 0 equals 1. That's how you'll actually write your answers in AP Pre-Calc. Okay. One more from me before, oh, no, sorry. I have 2 more for me before you have 1. All right, let's look at this one here. Let's type in this equation. Again, I'm gonna go clear my calculator. So home screen, new document. I hit don't save. I add a graph. This time our equation is going to be x cubed. Oh, tell me before I hit enter, what shape will this be? What type of polynomial is it? Is my question. Is it linear, quadratic, cubic? What is this one going to be? Cubic. Minus 3x squared minus 4x, which means it should look like a S-curve. Before I press enter, let's type in the restriction. How do I get to that pipe for the restriction again? Control equals, I'll choose pipe. Whoops. No. I don't know what I did, but I accidentally aired it out. Okay, here we go. Okay, control equals, let's do a pipe from -2, which is less than or equal to x, which is going to be less than or equal to 5. And press enter. Now I can't see the whole graph. One of the things you can do, I haven't done this, if you are going to use the calculator to zoom out without changing the axis, I want you to choose zoom fit and only zoom fit. Zoom fit, if you go to zoom, window zoom, what zoom fit does, don't ever choose zoom out. We're not going to change x's in our class, or if we will, we know what the x's are supposed to be. Zoom out will change x's. I don't want to do that. Zoom fit, if you notice, look at my screen. The arrows are going up and down. You see how they're going up and down? It only changes y's. It does not change x. So that's what, if you're going to use a zoom, you would do zoom, fit, and nothing else in my class. All right, what points do we see this time that this is going to have? What do you notice this graph is going to contain? The first thing is zeros. Does this have zeros? It has 3 zeros. And that's because, remember how I said if the degree is 0, you can have a maximum of 3 zeros. This one contains all 3 zeros. You will never have more zeros. Oh no. You'll never have more zeros than you have powers. Than highest power, I should say. You'll never have more zeros than highest power. Okay, I'm going to do this all 3 times. Menu, analyze graph, 0. I'm going to the left and right. And I'm adding these values in. Okay, I've added all 3 zeros in. The next one on there is minimum. Does this graph have a minimum? Yes. How many minimums does this graph have? 1 or more?
Good morning, Residential teachers. If you would at this time, please go ahead and submit your roll.
Okay, and this one has 2 minimums, so I'm going to find both minimums. And this graph has how many maximums? Does it only have this maximum over here? Or does it have another maximum? You see how this little area where we're concave down, you see how that's going to be a maximum in there. I need to find that maximum as well. This has 2 maximums. This point right here where we're concave down, that's a maximum. Okay, I don't know how to fit all these points in. But that's where it would be. Okay, I'm gonna copy this over. Cubic since degree equals 3. All right, let's start filling in the information here. As you look on this graph, do we have any zeros? Where, how many zeros do I have? 3. Where are they? -1, 0, and 4. -1, 0, and 4. You can just write it like this again because it's understood that the y will be 0. If you write it like this, f -1 equals 0, that's still right. You can write it like that. You just don't have to. You can write it simple like that. Okay, do we have any relative maximums? That means a maximum, but it's not the highest point in the entire graph. Does this have any relative maximums? We do. Adrian, where is it? It's this one. This is a relative maximum. This point right there, that is a relative maximum right there. The relative maximum is -0.528, which equaled 1.13. That was a relative maximum. That means it was a maximum, but it's the maximum of an area, but not the maximum of an entire graph. Now, as you search this graph, do you have any relative minimums? That means the minimum, but not the lowest minimum in the entire graph. Do we have any relative minimums? Yes, we do. Where is it? I'm going to do here R max is that point. This one, you're right. This is a relative min. Is this one. It's not the lowest on the entire graph, but it is a minimum. So we would say f of -2. Very good. Whichever student said that, I couldn't heard you, but wasn't able to make out who it was. Good job. Is that you, Miriam? Okay. Good job. Good job. Priscilla. All right. How about absolute maximums? Do we have any absolute maximums? Where is it? Where's the absolute max? 530. Very good. That's it. That means this is the absolute max. Okay, that's the absolute max. Do we have an absolute minimum? Yeah, this is it right here. This is the absolute minimum right there. That's the lowest point. So we'd say f of 2.53 equals -13.1. Is the function ever decreasing? Is there ever a part as you go left to right that the graph decreases? Yes, from where to where? From -0.528 from that maximum. It decreases up until this minimum, which is at 2.53. We decrease from there to there. Is there ever a part where this graph increases? There's actually 2 sections. So from first where? From -2 until when? Y'all tell me. Very good. -0.528. Now what you do if there's a second portion is you do a union. That's the symbol. That means there's 2 of them. Now where else do we increase? From 2.53 all the way until 5. 2.53 until 5. Are we concave up? Is it concave up anywhere? Yes, from somewhere in here. I don't know where. Let's just guess that's about 1. Okay, I'm just gonna round. It's concave up from approximately. And since I don't know exactly, I'm gonna do a squiggly 1. That just means I'm rounding. Now that looks like a negative, doesn't it? Let's not do that. I'll just go 1, 2. Where does it stop being concave up? Not 30. That's the y. You only go off of x's. You go off the intervals. Okay, where is it concave down? And you know what? I'll do that part in red since I know the 5 is accurate. What I'm not sure is if the 1 is. So that part I'm doing in green because that's a guess. The green's a guess there. Okay, what about concave down? Where is it concave down from? -2. Whoops. -2. There we go. -2 until approximately 1. So I'll do that again, green again, because I don't know exactly. I'll just put here. Guess of inflection point. At x equals 1. That's why I did that in green. I'll change that to green here in a moment. And so the inflection point, if we wanted to guess 1, what do we say that y value is? 1, 2, oh, I don't even know what that's counting by. I don't even know, and I don't think our calculator finds it. If it did, I would add it in, but it doesn't say. And so the best thing I could do here is I could add the point on the graph. No, that's not what I want to do. I could add the point, but I'm just gonna guess here. I'll trace it and find the guess. If I went to an x value of 1, oh, it doesn't even give me 1. It's gonna be approximately -6 or so. I don't know. I thought it would give me a better guess. It's somewhere between -5.3 and -7.9. So I'm gonna just say it's about -6. If y'all are okay with that, I'm gonna say it's approximately -6. So we're gonna say f of 1 equals -6. And that all that is a guess. Yes. Go for it. Go for it. And I'm gonna erase this and change it to just x equals 1 at 1 -6. I'll write it that way. So that's just a guess there. There's no way in our calculator to figure out what that is, and we're not going to take the time to do it by tables. All right, there's one more here, part D. Okay, so last time here, I'm going to go home screen, new document. I'm going to say don't save. We're going to go add a graph. I'm going to type in this equation, 4x squared minus x to the 4th. We're going to restrict the domain, so I want to do the pipe. And we're going to restrict it from -3, less than or equal to x, which is less than or equal to 3. Now this is going to be what we call quartic. It's the 4th power. You don't need to know the name quartic, but that's what it's called. Since the degree is 4, I know it's not the first power, but you're looking, the highest power is 4. You'd call this quartic. Since the highest power is 4. Now find the key values. I see there's zeros. Specifically, I see 3 zeros. Looks like we have a 0 at -2. That one looks like it's going to be right at 0 at the origin, and it is. And we have one more 0. At 2. This graph, it asks if there's minimums. It does have a minimum. I've already found. Whoops. You know what I have not done? I need to zoom fit this. Zoom fit to see if there's any other minimums. It looks like there is here. So let me go menu, analyze graph, choose minimum. Have this minimum. And this minimum. And then finally, maximums. We have 2 maximums I can see. Analyze graph. I'm going to choose maximum. I have this maximum. And analyze graph, another maximum. Now on this one, I'm gonna have to guess on inflection points again. All right, now that I have all that, let me pull this over to our notes, and we will complete our notes here. So I see 3 zeros. I have zeros at -2, 0, and +2. I have relative maximum, or do I have absolute maximum? Because this is the highest points on the graph, these are absolute maximums, not relative. I do not have relative, but I do have absolute maximums. I have f of -1.41 equals 4, and I do a comma, and I have f of 1.41 equals 4 as well. I have both of those two absolute maximums. These two would be absolute minimums. F of -3, and actually what you could do is say f of -3, which equals f of +3, which equals -45. You could also do it this way if you like. Either way is fine. You could write them separate or together like that because those values are equal to one another. Either way is acceptable. Do I have any relative minimum? I do. This is a minimum at the origin right there. It's a minimum because it's the lowest area, but it's not absolute, so it's a relative min. So at the origin, the function decreases from this maximum to this minimum. It decreases. So from -1.41 until 0. It also decreases from this maximum to this minimum. So from 1.41 until +3. So it decreases on those two intervals. This graph increases on the first interval from -3 to -1.41. And it also increases from 0 to 1.41. It is concave up in between here. Now I'm going to have to make a guess. And since this is counting by twos, I'm going to just guess that my inflection points are at -1, 2. Whoops. -1, 2, and +1, 2. That's what I'm going to guess for my inflection points. So I would say it's concave up only between here and here. It's concave up between 1 and -1 and +1. Between -1 and +1 is concave up. That's a guess. I'd say it's concave down from -3 until -1, and it's also concave down again from 1 to 3. Finally, the inflection points, I would say f of -1 equals 2, and f of 1 equals 2. So with all that, we've now completed lesson 1-4. You have, you have this DOL number 2 to take a look at. Determine the number and location of zeros, determine the number and location of relative extrema. You have DOL 3. Polynomial function has x-intercepts at 0 and 4. Which of the following statements must be true? After you complete those, you can go online to my AP Classroom and try your quiz there, a problems assigned.